Welcome to another GCBASIC demonstration. This one is a little bit of a deeper dive into the AVRDx, looking at how the internals are working and a bit more about the debugger. So this is really a backup to the previous video, but you just need to see the both to get the picture. So we've added AVRDx microcontrollers to GCBASIC. They're quite good. Performant, low power, low cost, easy of use. Okay. People should be using them. What I'm going to show you is a AVR 128 DA or DB. Is it DB? I think it's DB. It's DA because that's what it says on the box. 48. And essentially, all I'm going to do is go straight into and start showing you some stuff. Okay, so I'm going into GC code. This is our IDE, and from here I can program things. So I have specified I want an AVR 128 DA48. I said option explicit, so things need to be defined. And I've said that the port C6 is an output port, and I'm toggling that by using the not sign here, waiting for 500 milliseconds, and then doing it again within the do loop. Quite nice. I've just pressed function key F5, and F5 now downloads that into the microcontroller. Now, I've already said this in the previous video. Someone can help me work out why this stalls occasionally. It just stalls. It just stalls. I don't know why it stalls. It's nothing to do with our compiler. It's something to do with the utility. That the way that it's written. It's written in C. It just searches. There, it's done it now. Now, let's see if it's done it. I'm going to Zen mode. Zen mode looks like this, and I can open up a camera. There it is. It's flashing. If I change my delay here to 45 milliseconds, it will then flash a lot faster. There we go, a lot faster. And that's the camera that's doing that, it's not delaying, it's flashing quite nicely. Okay, some things you can do. In here, there isn't much information in this window here that's come up. So first of all, we're going to open that up by pressing the options. You can get to that by pressing function key F4, open up the preferences, and I'm just going to zoom in on the preferences, and I'm going to change the compiler to do some stuff. So I'm put it in verbose mode, show the GCBASIC source program as comments, blah, blah, blah. That's it. That's what I wanted to do, really. Back to Zen mode. Now, if I compile, I'm going to get a lot more messages. So I'm going to turn the camera off a second. So what have we got in here? Let me drag this window up. It says, these are all the libraries that are available by default. Not many of these are used in reality, but are always loaded. They don't take up any memory inside the microcontroller. They're there for references. And it says that it's found a chip file for an AVR 128 DA48, which is good. And it's set the frequency to 24 megahertz, which is the default. Okay, so specification on the chip itself. Then it's going through the process of defining what it's doing inside the compiler. It then writes it out. Writes that out to an ASM file, which we'll look at shortly. So it's written that file out. In actual fact, I'll come back to it in a moment, in 2.5 seconds. And then it actually assembles that in a few moments later using GCASM. Takes 0.179 seconds and it creates a hex file. Okay, so what stats have we got in here? It says it's used very little memory of the progmem, no RAM, and it did it at 24 megahertz. So you can get a full report of what's going on. There are fuller reports available, but that's the one that typically you'd be using. So I'm just going to come back into here. I'll zoom in on that for us, and just put that suppress summary mode. And I'm going to show you that now. Suppress summary mode. you get a little, and that you get this level of information. What I actually want is the one that's in the middle. I want the one that's actually got it turned. It's if you turn them both off, you get sort of an interim, a middle report. I better zoom in so you can see it. I've got verbose turned off and suppress summary mode. Press OK. Now I can. It gives me a bit more information in here, but not masses. It gives me the memory usage, and it says here 24 megahertz, and that's what I wanted to show you. So if I come up to my program here at the top, comma 16. Oh, I've just pressed F5. It says it's using the internal oscillator at 16 megahertz. I can put that at 24 divided by 48. Is that valid? I think that's valid for this chip. Oh, it's not a primary source. Look, it says ensure that it's not a primary source. You can run it. You just have to make sure it's set up correctly. 16. It just let me just have a look. AVR 128 D8. There's a. Oh, I can choose these. Look, any of these. Look, 20, 16, 12, etc., etc. And if I come into here and I put in 24 in here, it will do a calculation, and it will set the frequency for us to the correct frequency at the bottom, which I'll show you. It says 1 megahertz, and it's being calculated by the compiler. What I mean by that is it's done the maths for you. And if I look at the Zen mode, we'll look at the camera. It's still flashing at whatever 45. Forget how many milliseconds we chose. 45 milliseconds, even though it's running at 1 hertz, because it's done all the timing. It does all that for you. Let's look at. So that's important. You can see the detail, and you can change the configuration of the frequency, and it does maths to make sure. So on some of them, you've got some very strange frequencies, and it would be very hard to type in 3.16666 and get it correct. Just use some maths in the configuration on the chip line, which changes the frequency. Put that back to 24 and program it. And it's still doing the same thing because it's now running at 24 megahertz. Okay, I am going to zoom out, show the full screen, and I'm just going to start up Microchip Studio. Okay, Microchip Studio, you see it starting. I'm going to use this, I'm going to create another project. Now, I created one previously, but I will do the whole thing again because you don't see much on here. It's pretty hard to see this screen, okay, to be honest. So, File, New, Project. Then I'm going to have to move the screen around for you, or zoom out a bit. Oh, here we go. I'm going to call it AVR 128 V2 because I've already made one. And I'm going to use the assembly from GCBASIC, so I don't need to put it in C. I can just put it here and select it and press OK. Creates a directory for me. I'm going to put in my chip name, AVR 128 D848. Select it on the right. Now what it's doing is creating this empty project. On the right hand side of the screen here, I will move it across so you can see it. It's got the dependency files, which are required. It's got an output file, which is created for you, main.asm. And so what I'm going to do is I'm just going to, if you just build that, let me change the screen resolution. Hey, I think I can Get that on the screen there. Very good. I'm just going to minimize that. If I now build that and build that solution, it compiles it and successfully. Well, of course it does because it created that project. Let's go back into GCBASIC for a second, and we're just going to grab the source file, the ASM file. Control Shift F7, and here is the ASM file in its entirety. Control A, Control C, back into Microchip, into here, back into my source program, delete it, and paste that in. And this time, as different from the previous video, you can now see everything in green, which is the documentation of what it's actually doing. Project, just to build it, just to show you. You've got the warnings, which is fine because there's 0 errors and they're just redefined. They're redefined over here in the dependencies. This is the actual microchip file. So if I now, it's already connected to the debugger. It does that automatically because it detected it when I started up Microchip Studio. It said, oh, there's a microcontroller board sitting out there with a debugger ready. So if I go start debugging, it starts it straight away. We're actually looking at registers. We're looking at the processor status here. We're looking, I'll bring it into view here. This is the port C that we're going to be, oh no, that's the out. I want the virtual point C. And the chip isn't running. You might not believe me here. It's hard to show all this. Seriously, it's running there. Can I zoom in a little bit here for you? Let me unlock that for you. Unlock the screen. You've got the camera on there. We have our source program. We have the watch. We should be able to walk it now. So here we go. Press function key F11. It will now walk it. And these comments here in green are from GCBASIC. So this is setting up the stack. This is all the code that you didn't see. The only thing you actually saw was this in the if you don't have the comments turned on. It says here it's calling a function to unwrite protect. It's actually, there's a set of sequences you have to go through. That's all been done for you. So it's setting the frequency to 24 by setting up a register called, let me have a look, it's this one here, look. CLR control oscillator control a frequency to 36. Does all that for you. It just does it. And I'm walking the code here, and nothing much is happening actually out on the chip for obvious reasons, because it's getting debug signals in from, I'll get that LED flashing for you. You can see the NDebug flash there because it's communicating with it. And it said these registers are coming direct back in from the microcontroller. On the program, it sets the port C.6 to an output, and now it's going into the loop. Now, here's a dilemma. I'm going to put a break here. I'm going to insert a breakpoint, and I'm going to run it to there. Now, why have I done that? Is because this delay here in the, oh, no, we're on the real simulator. Let's just let it run. We can see it running. So it's in this loop. We have a do loop here, do loop. It's in that loop, and it's running it at high speed. And if we pause it, it's in the timing loop. That's and I'm just going to have to run to the cursor. It says here, look, it's the loop. Go back to the sysloop 1, which is automatically incremented by GCBASIC and managed. It says, right, I'm going to use a variable called system1. I think it's an R register. It gets the goes and gets that register. It compares bit 6. If it is off, it then would increment sys bit 1. It then copies that out. Here we go. It's now doing reading the existing value of port C, because port C has 8 registers. It says I want to compare C.6 against the value that I've already got, and then I'm going to copy out the correct state, and it turns the LED off, which is exactly what it should do. Now, if I put a break here, I can let this run, and it's come back. So let's do that again. It loads the current port C into this bit test. It's obviously a bit variable. If it's clear, it does one thing. If it is clear, it increments it by 1. Therefore, it just increments the bit on and off for you. Great. It then goes and gets the value of port C, compares bit 6, compares it to the number that I've got stashed away in system 1, and then sets it to that value. So you can do some very complex things this way. I'm only showing you flashing an LED, but it represents all IOs. Function key F9. So I'm walking the code. So I can make a change inside GCBASIC and just walk it across. I never use the debugger. I have to admit, I don't use the debugger. GCBASIC is robust enough. I just use the serial signals. Job done. I wanted to show you that in some detail. I'm going back to, or I better turn that off actually, because I can't program it whilst it's doing that. So I'm just exiting out from here, and it's leaving the program running. So what's different about these chips? Well, obviously the interrupt handlers are very different, and that needs to be developed further by the user community. But essentially, it's the transformation of what was bit orientated to OR orientated in terms of the IOs. So if we have the same program for an old microcontroller, we can see the difference. So let's turn the camera off. If we look at this piece of code here, port 6 out. It says, right, go and get the current state of the port C. Set bit 6 on sys value. Make sure it's set for me to 1, and then it copies it out. So it's got this ORing going on continually. And that's the difference. If I come into my program here and we look exactly at that piece of program here, and we'll do it on a 328p, and we'll look at this, we'll look at the code. I'm going to find it, what we were looking at. There we go. Here is the old command, port. It just set a bit. It said DDR RC. It had a bit register, and you could just set it directly. Well, you can't do that. So the trick is actually doing that translation inside the compiler, keeping the high-level language the same, because I didn't want to have that level of abstract be removed. You abstracted from the complexity. So let's do it again. This is for a Mega 328p legacy AVR. Start the main program, wherever it is. Here it is, down here. And you might say, well, that's not the way to do it. But if you've got a better way, tell me, and we'll change it. If I can write direct through and make it faster, I would happily do that. But I use the materials that they gave me. So if I look at the reference materials, the Microchip have done a pretty good job on migration, which is what I was reading. Oh, it's not that one. So this is the actual, there's a data sheet that you can read. Control B, get rid of that, get rid of that. This migration guide is quite nice. But essentially what it says is your your clock's different, which I've sorted. That's it. That was relatively simple. IO and pinouts. Here we go. So this is the old way of doing it. We've just seen that actually in use here. DDR. We've just seen this. And this is the new way of doing it. But if you need pull-ups, etc., it's very different. This is the old way. And here we go. Like in here, they say use the Z pointer. It's just way too complex. But essentially, what they're saying is here is use the Z pointer, use indirect addressing, load the address into the Z register, read the contents of port A, set it with a logical OR, and then write it back. That is 1, 2, 3, 4, 5. That is way more ASM than we've got at the moment. Okay, I'm sure there are easier ways of doing things. But this is not the way that I would recommend anyone doing it. It's not fast. So we should be a lot faster than this implementation, which is quite good. Okay, so let me just close that down, and go back to PowerPoint. If I can get back to PowerPoint, there we go. So what I wanted to show is a deeper dive into AVRDx microcontrollers and how it interacts with the microchip assembling tools and debuggers. Go enjoy.